Hi, I'm going to be working out the problems on pages 7 through 9 in the work and energy packet. So the first one is going to be number 11. Anything that comes before that was already discussed in part 1 of the video. So it says a 7 kilogram bowling ball moves at 3 meters per second. How much kinetic energy does the ball have? So all these problems are considered pretty easy. Okay, it's just basic formulas, right? So the basic formulas we're going to use is energy in a spring or elastic potential energy is 1/2 k x squared, k being the constant of the spring. I showed you how you can find it last time. Gravitational potential energy is m gh, and kinetic energy is 1/2 m v squared. So how much kinetic energy? You just have to do 1/2 m, which is in kilograms already. The v is in meters per second, and you can just do get your answer in joules. Because I showed you last time, we didn't talk about the units for energy, but I think it's understood that when you do work, your energy level changes. So either you increase or decrease your energy. So work will cause a change in energy, so energy has to be in joules. Okay, how fast must a 2.45 gram object move in order to have the same kinetic energy as the bowling ball? So if you do the kinetic energy for the bowling ball, you're going to get 31.5. Okay, so k is 1/2 mv squared. Well, you want this small object, this 2.45 grams, to have the same kinetic energy. So you put the kinetic energy here, 1/2. Now you have to change grams to kilograms. And then you would just do v squared, which means this has to be moving extremely fast because it has to compensate for its lower mass by going fast. And it's 160.36 meters per second, a lot faster than the 3 meters per second we had earlier. All right, number 12. Two bullets have masses of 3 grams and 6 grams. Both are fired with the same velocity. Which has more kinetic energy? So here I think we should just compare them basically, right? Kinetic energy is directly proportional to mass, and it's proportional to the square of the velocity. So I'm not going to change this to kilograms, just comparing. So when the mass doubles, the kinetic energy will double. Now, what's the ratio of their kinetic energies? It's 1 to 2. How is kinetic energy related to mass? It's pretty direct. Okay? There's no squares, nothing like that. It's very linear and direct. All right. Two identical bullets are fired, one with a velocity of 40 meters per second and one with a velocity of 80 meters per second. Which has a greater kinetic energy? Well, they are identical, so the mass is the same. Obviously, the one that's going faster is going to have more kinetic energy. Now, the ratio, you can do the work, but you can see that since the kinetic energy is directly proportional to the square of the velocity, so when you go from 40 to 80, you're doubling the velocity, so your kinetic energy would be 4 times as much. So, and I just talked about how is kinetic energy related to velocity. Kinetic energy is directly proportional to the square of the v. In other words, if you graph kinetic energy versus v squared, you should get a line, right? Okay, and the slope of that line is 1/2 m. All right, number 14. A spoon is raised 21 centimeters. Okay, you gotta be careful with that, above a table. So now we're talking about changing the position of the spoon. So which means we're talking about gravitational potential energy. If the spoon has a mass of 30 grams, you got to be careful, got to change that later. What is the gravitational potential energy? So the question is simple. The only problem you have to be careful with your units. So you have to change the mass to 30 times 10 to the negative 3. We're going to go with 10 for the acceleration of gravity, and the height is 21 10 to the negative 2. And should get an answer of 0.063, which actually makes sense because it's a light spoon and you don't have to raise it very high, so you don't need a lot of work to do that. A spring with number 15, a spring with a spring constant of 5.2 newtons per meter, it means you need 5.2 newtons to stretch it 1 meter. In other words, you're going to hang about 0.52 kilograms on a spring if you're going to hang it vertically so that it stretches 1 meter. Has a relaxed length of 2.45, meaning like this is before you stretch it, before anything is put on it. When a mass is attached to the end of the spring and allowed to come to rest, so basically this is what it is. Okay, when there's nothing on it, this length here is 2.45 centimeters. Well, you hang something on it, or you stretch it, a mass is hanging on it. So when you hang something on it, the spring is extended to 3.57. So this is 3.57 centimeters. Calculate the elastic potential energy stored in the spring. So we're only going to look at the amount of stretch, right? So US is 1/2 kx squared. Well, the k is 5.2. Now, the x is basically the difference between 3.57 and 2.45, and you must change that to, what do you call it, centimeters, right? So I can do something like this. I can do 3.57 e to the negative 2 minus 2.45, 10 to the negative 2, and I can square all that. And you should get 3.26 joules. So you just got to be careful here. We're only looking at the amount of stretch from the non-stretched, the unstretched shape. And I think so far the only issue could be the units. So you just got to be careful with your units. Jane stands on the roof of school holding her egg drop project. We're going to do an egg drop project later. If her device has a gravitational potential energy of 460, calculate the mass of the project. Well, you pretty much have, this is too easy. 460, we need to find the mass. This is 10, the height is 12. That's a simple equation. What is the work required to extend an exercise spring by 45 centimeters if the spring constant is 310 newtons per meter? So with that spring, in order to stretch in 1 meter, you need 31 kilograms. 31 kilograms is about, just roughly about 70 pounds, right? So it's a pretty stiff spring, just looking at the number. All right, so the work required to extend it by that much is basically going to become energy stored in the spring. So instead of finding the work, it's the same thing as finding the energy that's going to be sitting in that spring, stored in that spring. Okay, so this is going to be 1/2, 310. Now you just got to be careful. You got to change the centimeters to meters, right? I don't want to see that mistake on the test. It will be a shame. Okay. And that should be about 31.39. A 50-kilogram gymnast stretches a vertical spring by 1/2 meter when she hangs from it. How much energy is stored in the spring? Now we don't have the K, so I think we can find it, because what happened is, okay, when this person, I'm just going to draw it as a box, is hanging from it, when this is at rest, the forces acting on it should be equal. So this is the force of the spring pulling back, wanting to go back to its unstretched shape, and this is the force of gravity pulling the person down. So those two have to be equal. So Fs, I remember I showed you that the magnitude of it is just Kx. This is mg. So I think we should find K first. So the mass times g, that's 500 over 1/2 meter. Okay, so that's about 1,000, right? Newtons per meters. I think I missed one earlier. All right, I'll go back to number 18. All right, so the spring constant is a 1,000. In the answer key, I did it differently, but that's fine. So the the energy stored is 1/2 kx squared, and that's going to be 1/2 of 1000 times 0.5 square. So the answer at the end is going to be 125 joules. You can look at the answer key on Haiku. I did it slightly differently, which is it's really the same thing. So just I manipulated the algebra differently. A spring requires 46.1 joules of work to extend it 12 centimeters, and 278 joules of work to extend it 27 centimeters. Does this spring obey Hooke's law? In other words, Hooke's law is F equals Kx. Okay? And there are limitations to these springs. If you overstretch it, it no longer obeys this rule here. It just like it doesn't come back to its natural state. So in order for it to obey Hooke's law, the K has to remain constant. So basically, we have to see if we have to find the US, and that's 1/2 kx squared, right? So I think we should find the K when it stretches 12 centimeters, find the K when it stretches 27 centimeters, and just compare the two, which is the same thing as basically finding this ratio here. Okay, so the 2 is common to both of them. So basically, I'm going to see if this is constant. So I just have to compare those two. If that's a constant, then it obeys Hooke's law. If it's not, then it doesn't obey Hooke's law, right? So the K has to remain the same. Now I'm going to do the last problem. A student suspends a 0.25 kilogram mass on a spring that stretches it at a distance of 5 centimeters. You got to be careful there. The student removes the mass and pulls down the spring, stretching it and doing 10 joules of work. Now that's not a lot of work. So I think the first thing, how far did the spring stretch as a result of the student's work? Well, I think we have to find the K. So when they stretch it, when they hang something on it, let's just say the first dotted line is the unstretched shape. It stretches by 5 centimeters, which translates to 5 times 10 to the negative 2 meters, or 0.05 meters. So this mass here is 0.25. Again, the spring is pulling back on the mass, gravity is pulling down on the mass, and those two have to be equal. So Kx, which is Fs, should be equal to mg. So I'm going to go ahead and find K. K is 2.5 divided by 0.05. And we're going to number for K. How far did the spring stretch as a result of the student's work? Well, US is 1/2 kx squared. Now this is going to be 10 joules equals 1/2. And we put whatever we got from here, which I'm going to cheat a little bit and look it up. That's about 50. No, don't feel like doing mental math this morning. So, and put x squared here, and you just find your x. But when you find it, you're going to find it in meters. So it's about 0.63 meters. And if I look at my everything that I got in my calculator, it's about 63.25 centimeters, right? Okay, and that's it. So it's extremely simple stuff. So you just have to be careful with the units. Otherwise, the math is very straightforward. It's very linear. Okay, I'll see you later.